Hello, and welcome to the Spatial Model tutorial number 2. The current video is about getting acquainted with the spatial model objects. In doing so, we will get to know the main components of the spatial objects, which are pairs, triplets, and forks. We will learn what each one of these objects is designed to do and what type of alarms it can trigger. The first object is a pair. The pair has a source and a destination station, and it constitutes the most basic object of the spatial model. In a pair, water flows from the source station to the destination station. The pair looks at the value variability of a given quality between the two stations. The pair performs two tasks. The first task is a duration of flow estimation between the source station and the destination station. The second is a quality variable estimation of the value at the destination station based on the historical values at the source station and the flow duration. Each flow regime has a flow duration estimation. As of the current version, flow regimes vary in the following situations. Weekdays have a day and night regime. And on Fridays and weekends, other regimes result in more up-to-date distribution of regimes throughout the day. An explanation of the flow regimes can be found in the appropriate training section. How is the flow time estimated between the source station and the destination station? The system divides the collection of records selected for study into groups called bins. The system calculates for each bin the average value of the selected variable. These values form two time series, source station, and destination station series. On the chart before us, they appear as the blue series and the red series. After they form, the system calculates a correlation coefficient between the series multiple times. Each time the source series moves in time for the target series, it is reflected in the number of minutes sliding. The correlation coefficient is calculated for each sliding. The collection of sliders and adapter coefficients creates the score function. This function is displayed at the bottom of the slide. The sliding value with the largest correlation coefficient is the value selected for the time regime tested. After calculating the flow time between the source and destination stations, the pair can begin to predict the measured value at the destination based on the historical measurement at the source. For each new record at the target station, the model calculates the predicted value based on the appropriate historical value. The graph before us shows both predicted and measured values. The blue series represents the actual measured value, and the green series represents the predicted value. Both sets refer to the destination station. Besides, the model calculates two additional values, upper spatial boundary and lower spatial boundary. These two values are shown in the graph in front of us as the top and bottom gray lines. When the actual blue value crosses the upper gray line or the lower gray line, a spatial boundary violation is detected. This violation means that something happened to the quality between the source and destination stations. The system generates the above type of alert, as well as other alerts, after a delay of time to prevent false alerts. Another alert that may be received is ineffective spatial boundaries. This alert is the ratio of spatial boundaries to static boundaries. The value of the distance between the statistic boundaries is shown in the diagram by the orange arrow. The value of the distance between the spatial restrictions is shown in the graph by the gray arrow. The division of one in the other gives the relation between spatial and static boundaries. In normal mode, this value should be less than 50%. When this value exceeds 50%, you will be notified of ineffective spatial boundaries. The 50% value is the default and can be changed by the user for each pair individually. A third alert that can be produced by the pair in the spatial model is an error of prediction. To calculate this error, find the difference between the predicted value and the value found, represented in the graph by the gray arrow, and divide it by the actual measured value represented in the graph by the blue line. The system will notify when the deflection is greater than 25%. This value of 25% is also a default setting that can be changed by the user. and a last and fourth alert is a lack of data. This alert is valid when the source station or destination station has no data for calculation. All the displayed alerts are transmitted after the delay time to the EDS system. An explanation about transfer can be seen in the chapter on the relationship between the spatial model system and the EDS system. What is the connection between the pairs alerts and triplets alerts? This connection has two meanings. First, an alert in a pair usually will consequent an alert in the triplet containing the destination station. If this is not the case, that might be evidence that the pair is not calibrated correctly. The higher the number of alerts in the triplet's destination, the more reliable the pair's alarm. On the other hand, an alert in the triplet and no alert in any of the pairs containing the triplet's stations is possible. This situation is possible because the triplet's mechanism is more sensitive than the pair's mechanism. A condition that you see in the triplet may appear before it appears in the pair. Explanations of these phenomena can be found in the model's algorithmic documents. We hope that this tutorial was helpful. If you have any comments, please update in our website.